I want to spend some time to discuss the communication protocols in database systems within the context of the web and the three-tier architecture in general, and how that web and REST and the three-tier architecture have changed the way we communicate to the database. And personally, I think we need to pay attention and revise this communication that was initially designed to be one-to-one client-server, peer-to-peer, where the client is the final consumer of the database. There is no additional hop. And I wanted to talk through these points that I have in my mind and how multiplexing, the technology of multiplexing in general, with regards to how we have improved the web with multiplexing, with the idea of HTTP2 with Speedy, and then we moved to QUIC as a general purpose protocol, and how, not really how, just does QUIC or does multiplexing help a three-tier architecture to give you more throughput, less resource consumption on the back end? And finally, will the database even handle the increased concurrency as a result? I'm going to discuss all of that in this show. If you're interested, stay tuned. Welcome to the Backend Engineering Show with your host Hussein Nasser, and today's episode is a very interesting one. I have discussed this topic many times in this channel, but every day I gain a little bit more insight that kind of makes me go back and revise my statements in the past. And this is basically the communication protocols between the client and the database. And we don't really have something other than TCP, the beautiful transmission control protocol, TCP/IP. Pretty much all databases eventually use that as a method, as a medium of communication between the client and the database server. And when I say database server, I mean a DBMS, a full-fledged DBMS that supports multi-user features, right? Because a database system by itself can be a standalone engine that has nothing to do, that doesn't have a feature that allows other external clients to connect to it. It could be a single user like Lite, SQLite, and or my RocksDB or Levels DB, right? It could be like this single instance that you can just instantiate and run right to locally. But in this video, I specifically want to talk about the communication layer between the database and the server. And it's very interesting because it all started with just thick clients wanted to connect to the database directly, right? I built a lot of applications this way back in early 2000s, right? You have a C# Windows app, that's desktop app that connects to a back office database. You are in the same network, or you're behind some sort of a farm, Citrix farm that kind of abstracts away that thing. You remote in and connect things on the back end. But the idea always have been this thick app that the users, desktop app that the users interface with. And then every user would log in, would have an actual database user login that they log in with in the application. So that's why we needed database users log in to begin with. That's always have been the case. We provide that login and I log into the application, and now all of a sudden I have a session between my thick application and the database server. And I execute queries, I do all that fancy stuff, right? And we do all these tricks like, okay, I want to do concurrency, I want to do multi-threading. So we would, in the app, in the C# app, or any other language really, but I built Windows application for a long time, so that's what the example I give. You would spin up multiple TCP connections to your database, and then concurrently execute multiple queries if you're smart enough. If you want to like load multiple views or load something asynchronously, you can do that, right? Instead of running multiple queries synchronously on the same socket. That's just because to avoid waiting, right? It's like if the queries don't have anything to do with them, we can just execute multiple ones. And it's been working for a long time, right? TCP is basically the main medium for this. And I know other databases build their own protocol on top of TCP, but like I know Postgres has their own binary protocol, Oracle has their own OCI thing, SQL Server has their own stuff, and they also support name piped. Redis have their RESP, I believe, right? I forgot what it stands for. The binary protocol, their partner MongoDB have their own, but essentially I even made a lot of videos using Wireshark to see how those protocols look like and in wire transfer, but eventually everything uses TCP, right? And there's this application connected to it. And so you as a user, you were given a database user with specific permissions to access certain tables. You were not giving any DBA, right? You would create a user, and that user will access certain views, certain tables. The DBA will do a very good job here to kind of limit permissions, because very critical. You don't really need to have access to everything. That's just ugly, right? So some databases go further and have idea of SAML authentication in the database, like SQL Server, so that users have single sign-on, right? Once you log in, we're gonna pass in your Windows login all the way to the database. And when we do that, you don't have to have a separate login for the database, right? So we still, up until this point, we have not discussed the web architecture, right? Once the web came into the picture, things changed, because yeah, I still need a database to query, to put my blog post, right, like WordPress, and I need to query that. But wait a minute, now my users hit a URL on their browser. Does that mean I should give a login, the database login, all the way to the user? Nobody talks about this stuff. We just take it for granted, right? That's why I wanted to kind of talk about the elephant in the room and just discuss this stuff, because nobody talks about this stuff. And obviously that just sounds ridiculous, right? We're not going to create a database user for every single possible someone to visit with your website. That just, it's a DOA. It's a dead on arrival, right? You can't possibly scale that architecture. It makes me think, okay, what should we do? So people resolve to this hack. Okay, let's introduce this. Let's just have a set of users, that database users that are just dumb, with very long password that nobody will use to actually connect. But this will be our web application connected to the database, right? Maybe I shouldn't have called it a hack, but it feels like a hack to me. I don't know how I describe it, but technically the application, the web application, is a user now, right? And when I make a GET request to my web application through Express or IIS or Apache, PHP, anything, my web app will turn around and call the database and what it needs to connect, right, to the database. The user doesn't have this credentials, so the database now, the application, have this database credentials baked into it. That's something we never done before. We usually give the user, it was almost like an end-to-end with the thick application model. The user have the password, they log in, and immediately it's end-to-end. We don't really care. We don't store the databases users anywhere because we don't have to. The user have them, right? Now, all of a sudden, we had to persist this somewhere for the application to read from, for the application to actually start, right? That's, to me, that feels like a flaw. You might disagree with this, obviously, but, and feel free, let me know in the comment section or just ping me. This is a very interesting discussion to me. I don't know. Now, and we see all this kind of hack that happens. Oh, someone pushed the user password accidentally to GitHub and someone got it and they were able to access their databases on the back end, which is terrible, by the way, right? You never expose the database to the internet. Now that we are in the 3-tier model that we talked about here, where we have an application, a web application in the middle. The backend is the database. The web application is in the middle, the second tier. And the first tier is what? The client itself, right? The application browser or your Python script that hits your web app, right? It's very interesting thinking about all that stuff. So, but that's what we have today anyway. I just wanted to look at this with a pragmatic eye, just like, let's just discuss this. And is there a better way of doing things? Feels hacky to me. I don't know. I'm speaking really, I didn't prepare for this episode or anything like that. I just I like to speak organically and raw like that, because that's the original thoughts that I have. Because if I curate everything and edit everything to perfection, you get, I don't know, you get artificial show from me. I like to have my actual thoughts, and maybe as I talk, I kind of reconcile these thoughts. But you get to see the process, and that's the purpose of this show. You don't get to see like an advice, right? Hey, do this. No, it's a conversation that we have engineers. We crave these kind of conversations. We are not having this conversations anywhere, unfortunately. So that's what we have today. The application, the second tier, this middle tier, is the one that connects to the database, right? And it is the one that has the usernames. And now all these questions now, it's like, because what if I have 1,000 users? Does 1,000 viewers, 1,000 people who visited my app, do I spin up a TCP connection for every single viewer? No. Because remember, in the thick application model where we have a client and server, there is not a lot of servers. There is just few users. There's just one, right? Or multiples, and every user have almost like a one connection, and that's okay, because we don't have the model where we have a web app where we have thousands and thousands and even millions of users connecting. Now it's a different story. We have scaled so far. Clients have become so thin, they spin up and multiply so quickly. We have to think about this. The amount of requests that can come is just huge, and it is impossible to establish a single TCP connection for everyone. So we had to trade off. We had to trade off horses. First, let's go with with the singleton TCP connection model, because I've seen applications like that because they are terrible, right? A single TCP connection model, and every single client executes on this TCP connection is bad idea. That's why we moved from pipelining in HTTP. People just don't realize that until they get an actual nasty bug. When you start using a single TCP connection on between your web application and the database, and you have thousands of clients just hammering your web app, if it's like Node.js, it's asynchronous, is gonna start just pushing queries on the same TCP connection, and you're hoping that the TCP stack is gonna give it to you in order. Well, if you send request 1, request 2, request 3, right? The application, the backend database, will receive them at request 1, request 2, request 3, but you have no idea which one will finish first. Request 3 might finish first. And if request 3 finished processing, that SQL finished processing first, it's going to respond to the socket. It's not going to wait. It doesn't know to wait. It's going to respond to the single socket. And your web application is also dumb because, hey, I got a response. It thinks that request 3 that we just received belongs to request 1. The response number 3 is all of a sudden delivered to request number 1. Terrible model. All of a sudden you have leaks and stuff. Like, yeah, that's just bad idea. Query number 1 gets the result of query number 3. That's why we never ever execute 2 queries on the same TCP connection at the same time in parallel. We don't do that. We execute a query, we wait until we get a response, and as long as we wait, that socket is busy. We just mark it as busy. That is in use. That's how pooling works, right? That's why we invented the idea of pooling. Once you execute one query on that TCP connection, it's bad idea to re-execute another query while that query is processing, because you don't know how the database is going to respond. That's why we have all this HTTP 1.1, the whole thing, right? With pipelining, we move to a model where we have separate streams or separate TCP connections, will then replace with multiplexing. We're going to talk about it in a minute. But yeah, the idea of having one TCP connection that serves multiple front-end clients is a bad idea. So that's why we have the idea of pooling. What is pooling? Pooling, database pooling, is the idea of having, when the web application starts, it just established 20 TCP connections to the database and just have a state marked with every connection in the application itself. And most clients support this, database clients supports this idea of pooling. Now you have 20, for example, or you can configure this, right? You can go up and down. You can have maximum of 100 TCP connections all the way to down like 20, whatever. You can configure that. Now, as you receive request on the viewer, right, from a viewer in the web, you will, if that request require a database interaction, you would pick, the web application would pick a connection from the pool, execute the query, and mark that connection as in use. That's how pooling works. The next request that comes, as long as that connection is busy, the next request that comes in, it picks another TCP connection. It never picks that same TCP connection because it's busy executing stuff. You don't run its stuff again. Bad idea, right? So you pick another one, right? So until you hit that 20, if all of them are busy executing these queries, right? Then their next request that comes in has to wait, right? Based on your configuration, you might decide to configure your pooling instance to spin up another TCP connection and then reserve that up. And then you you'll play with that, right, up until you reach the maximum. Okay, and if an instance is freed, if a connection is freed, you can then serve a request to that freed index, and that's how pooling essentially works. So it's a beautiful design. Okay, however, it's expensive, right? Because now the idea of having pooling, first of all, you have to preheat these connections, because if you preheat them, if you don't preheat these connections, when I say preheat, I mean start them early, right, to avoid the problem of cold start, which serverless applications now suffer from, right? That's the major one of the major problem in serverless architectures, the cold start, right? How fast can I start up an instance? How fast can I start up this connection? The connections is not fast, right? I gotta establish the TCP handshake, the three-way handshake, and then obviously you're gonna, if you're on a cloud architecture, you're gonna do a TLS because you're gonna encrypt that stuff, right? You don't want to send stuff unencrypted. That's a bad idea, especially in a cloud architecture where you have this people in your network kind of as the same, almost the same network, and they can't technically sniff it in the physical layer. So you don't want to do that. You have to encrypt stuff in the cloud. I mean, cloud providers, I think, when they use this software defined networking thing, I don't know much about it, but it's a layer of software that actually abstracts the underlying hardware, right? So you can do all that jazz. I think it encrypts it by default. All right, yeah, the network Chuck have a great video on that. I believe he interviewed one of Verizon's engineers. They talk about how software defined. Well, follow the network Chuck. Great videos. He has great videos. So now we have those. We talked about the pooling, right? Now what's next? Pooling is great, but we talked about the cost of establishing a TCP connection. We talked about also another cost is not just the startup, the memory cost, because now you have multiple connections, right? You have to keep them running in memory, so that cost is depleted from your web application instance, because you're gonna establish this X amount of TCP connections. Plus your CPU has to work harder to work with multiple TCP connections. Plus there's something that is happening underneath you, which is the idea of mutexes and locking across these connections itself, right? How do you, if you want to build an application where you're gonna mark a state in every single connection, how do you do that, right? How do you mark a connection as stable, or this is in use, or this is unhealthy? How do you do that? You might say, Hussein, I'm gonna build a map or dictionary. But how can you guarantee that no two threads accessing that 7 and then set it at the same time, right? You might set it as in use at the same time someone thinks it's free, right? This concurrency race condition is the ugliest problem to solve in computer science. So you have to obtain mutexes or reside to a single threaded model where you sure that only a single thread can access this thing. Okay, it's complicated. I'm not saying the next solution that I'm gonna propose, which is I don't believe any database actually use, or maybe for a good reason. Maybe smart people discussed this already and decided it's a bad idea. But the idea of moving to a multiplexed version of the whole thing, where you build a protocol or you use a protocol that supports multiplexing into a single connection, right? HTTP2, right? And before you start, DBS is gonna yell at they're gonna yell at me, hey Hussein, we don't use HTTP and DB databases. Yeah, I know, overhead and all whatnot. But take the idea of that and maybe move all the way to QUIC. And the idea is here we have a single TCP connection, and we multiplex request into that single TCP connection. You might say, Hussein, didn't you just tell us you can't send multiple requests in the same TCP connection? Well, you can if you build the infrastructure around it. If you tag every request with a dedicated channel, or sometimes called stream, then you have a dedicated stream that you can dedicate for every single request in the same TCP connection. And the idea is not magic, it's just literally building headers upon headers on top of the TCP stack so that your application can identify, oh, this request is for this stream or this channel. I like the word channel better than stream, in my opinion. That's how HTTP2 works, the idea of streams. You have multiple streams. And HTTP2 was built because of a need in the browsers, because we found out that we can't obviously send multiple HTTP requests on the same TCP socket in the browser to like load an image and then load an HTML and then CSS. No, we can't do that. So we either spin up multiple TCP connections, same the problem as the pooling. We have the same exact thing. Software engineering is not magic, guys. It's the same thing happen if you actually looked into what's underneath, what's the first principle. It's all identical, no change. Once you add Django and Mango and Fango and Flask and React, this is where it gets fuzzy, because it's all abstraction built upon these fundamentals. If you just live in this husk of frameworks and you don't understand what's underneath, you will be lost. If it's not in a year, you're going to be lost in 2 years. Do not just learn the shell of the husk. Learn the basic fundamental, and you will see that everything will just make sense, because you're just building up. It's like memorizing every possible combination of multiplication. It's like, oh, 7 plus 8 is this, and 8 plus 7 is this, and 9 plus 8. Imagine memorizing every possible addition. You can't, right? You have to know how addition works, and then based on that, you build up and repeat. That's a silly example, but you get my point. But the multiplexing natures here has been in the browser for a long time, and HTTP1 is still used. HTTP2 tried to solve that by having a single TCP connection and marking having these logical streams or logical channels where you send requests in the same TCP connection but marked. They are just, think of it like it's marked. Oh, this is actually request number 700. So if something come back, the server is responsible to tag the packet, to tag the response with the stream number, so that we know, oh, this is actually stream 700. So that you can't just assume things are the way it is. Right? Order is not guaranteed at all. I mean, order is guaranteed in the TCP stack as packets, but order within the application layer is never guaranteed, because you have no idea when the server responds to all your requests, right? It's very, very interesting, these kind of discussions to me. So multiplexing, HTTP2 solved it. We came with another problem, so that I don't have time to cover in this show. But we solved these problems with QUIC, mainly the head of line blocking and all that jazz. We solved it with QUIC. I say we. I didn't have anything to do with it. People way smarter than me did. So QUIC solved this with UDP. They said, okay, TCP is just too much for us. TCP is trying to be too clever. We don't want clever protocols. Let's move down the stack and rebuild things up. That's what QUIC did. Move down the stack. They picked UDP, which is like this stripless, just send a packet, and then they built the guarantee, the packet guarantee. They built in stream inside it. They built in connection, logical connection in it. They built in TLS in it. The idea of they did that, this is just genius, right? They thought about that. They kind of hit two birds with one stone, fed two birds with one scone. So Peter, don't get mad. And You get the idea, right? We have moved, and now QUIC is popular, HTTP2 is popular, right? And now we have one connection or fewer connection. You don't want to put everything in one connection. Now less resources. So now I have few connections and I can multiplex this stuff, right, into this single logical connection. Let's say QUIC for simplicity. Now, can we bring this to the application layer, to the web application layer? And can we use QUIC as a way for my application to multiplex all these requests that comes in instead of using pooling? Maybe. How much would that solve? How much does that really improve the performance? I really don't have numbers. Will that help? It really depends. But it's worth experimenting with this, I believe. It's not easy because no database supports QUIC today, or no database supports the idea of channels, right? Because all DBMS systems today support their own TCP protocol that is designed to have a single client in mind. They don't build it so to have multiple clients in a single TCP connection. They don't do that, right? Right. RabbitMQ, for example, they built this with that in mind. They had, okay, yeah, I might have one connection, but I might have multiple channels. I love this design. SSH, same idea. They have multiple channels in the same TCP connection. So it's a very efficient way of delivering communication between the client and the server. And I think it's gonna give us more throughput. What I believe we will suffer from is the more throughput we get, I don't believe the databases at their current state can handle this much throughput. In my opinion, we've seen it. Most databases, they say, hey guys, when you do pooling, don't set this as an unlimited. Set a maximum number of connections so that you don't just hammer the database connection with so many TCP connections and so many requests. And you might wonder why. Well, can we just add more cores? Can we do horizontal scalability? Can we do all that jazz? First of all, I'm not going to talk about horizontal scalability when it comes to write. That's just a very difficult problem to solve, in my opinion. I know Spanner did a great job with atomic clocks there. And there are databases, other databases, I forgot the names. They're doing FaunaDB, I believe. They did great jobs at trying to kind of scale right horizontally. But the idea of having multiple requests and multiple connections simultaneously, concurrently, in parallel, databases don't like that. And the reason they don't like that is the acidity nature, and I just invented this word, acidity, which is the acid, right? The acidity nature of databases. To be an ACID compliant database, you really have to maintain concurrency. And when you maintain concurrency, what does that mean really? One part of concurrency is the idea of MVCC, multi-version concurrency control. And if you just sit down and think about the work that the databases do, you're gonna appreciate the work, and you're gonna understand why it's a bad idea to have this much clients connecting to the database, sending all these queries, specifically long transactions. We don't really mind short transactions. Long transactions are the one that kills the database performance. And the main reasons is we can't get it. This episode is going to be like an hour or 2 hours if we're going to discuss that stuff. But main things, and some of the stuff is just like way beyond my head, right? The idea of locks, right? as you edit rows in transaction 1, that row is locked exclusively so that we don't allow other transactions to mutually edit the same row. You can read it, right? But you can't edit it. And now this same question now. You just edit that row. You changed that layout of that row. You edited a field, employee, the salary. You changed the salary from 200,000 to 300,000. Wow, what a raise. Now, what happened to transactions that are already running? What do they see? Do they see if transaction 1 is changed to 300 and didn't commit yet and still doing some stuff on the background? What do transaction 0 says? What do transaction 3, which just started, sees? Does it see the 300,000 or does it see the 200,000? Of course, it's gonna see the 200,000. Otherwise, it's not asset, right? You need the idea of having concurrency and the ability to read, to be isolated. That's the correct word. The asset, the I in the asset, isolation. You need to be isolated. So the database need to keep a version of the old row. And now every database does this differently. In Oracle and MySQL and MariaDB, there's something called the undo log that is literally keeps the old version in an undo log so we can undo the changes in case of a rollback, right? So that means older transactions or newer transactions that have been started after the fact and are still not committed, they need to repack this undo log and apply it to the row in order to see the changes, right? Because these kind of databases like Oracle and MySQL, they change the final representation of the actual row to say it's 300,000, right? So if you have a long transaction and you have this change, this transaction number 1 that changed the row to 300,000 and remain running, thousands and thousands of new transactions that starts, and every request is a transaction by default, right? Whether you like it or not, we start the transaction and we commit it immediately, even if you have a single query. That has to always do that work, which is the undo. Go to the undo stack and then pull it back up and then kind of roll it up so that gets the actual 200 value, 200,000. While Postgres does this differently by actually keeping the row as it is and adds a new row, literally copies and pastes a new row that has its own ramification. There is no right or wrong. But regardless of what approach, it is expensive to maintain isolation. Imagine hundreds of thousands of transactions executing, doing this kind of thing. The database is going to do a lot of work. Every edit has to do this thing. Add to this locking. The idea of having this row is locked. How do you know this row is locked? There is information about the lock itself that the database has to read for you in order to block you. It's a very complex system. And having QUIC on top of all this thing, again, I'm kind of contradicting myself here, right? If you think about it, I'm not saying that QUIC is the solution or HTTP2 or multiplexing in general is the solution for this, but having increased number of requests, all of a sudden, concurrency will suffer, performance will suffer as a result. Doesn't mean that you just enable multiplexing, everything is just dandy and happy. Lucid Charts, a company that produced chart. I used their product a while back in 2012. They decided to turn HTTP2 on their backend. And their CPU cores shot to all 100%, all of the machines, all of a sudden. And their backing got slower as a fact. Because when they enable HTTP2, they didn't put an upper limit to the maximum number of streams they can multiplex through. So as a result, the clients just felt more throughput flood through the pipeline. You got more requests. That means more load on the back end. And as a result, the CPU has to work harder to parse the TCP stack at the application level in order to understand that, oh, this request is stream 1, or this request is stream 3, or this response is stream 700. It needs to do work that it didn't have to do before. So I'm going to pass the question back to you guys. Do you think multiplexing is a possible solution for this inefficiency that we have in the backend? Let me know in the comment section below. I'm going to see you in the next one. You guys stay awesome. Goodbye.